If you follow the world of large language models, you know there's one specific giant computational headache that constantly limits innovation, processing extremely long texts, what we call long context.
Yeah.
As the sequence length grows, the computational cost doesn't just grow linearly. It explodes. It's quadratic scaling.
Yeah, it gets exponentially hungrier and slower the more info you feed it.
Mm.
It's really the ultimate ceiling on model efficiency right now.
Exactly. Trying to get an LLM to read, say, an entire legislative history or analyze a huge technical manual.
Or even just maintain a really long conversation over time.
Right. The infrastructure costs, the latency, it all just becomes prohibitive.
But the source material we're digging into today, this technical paper presenting DeepSeek-OCR, it introduces a radically simple idea, but profound, to sort of bypass this limit. They call it context's optical compression.
Optical compression. Okay, it sounds maybe a bit like science fiction, but it's remarkably straightforward, isn't it?
It is.
So the mission for this deep dive is to explore how converting dense digital text, which, as we said, is computationally expensive, into a visual format, basically just a high-res image of the document, how that drastically cuts down the data load.
Yeah, the core insight is treating vision itself as an incredibly efficient compression medium. It's kind of counterintuitive at first.
It really is.
And look, this isn't about small incremental gains. The headline finding, the real shock factor here, is that this method, converting text to an image and then back, it can achieve near lossless text decoding. We're talking like 96% accuracy, maybe better.
Near lossless?
Yeah, even when the original information has been compressed by 9 to 10 times.
Wow, okay.
That is the kind of efficiency breakthrough the LLM world really needs for truly scalable, ultra-long context processing.
It definitely grabs your attention, 9 to 10 times compression. But before we dive into those numbers, why images? Why did they even think using pictures was the right way to go? Why does a picture of text compress better than the text itself?
Well, it really comes down to token efficiency. When we talk about optical compression, what we mean is leveraging the visual modality, that image of the document page, to represent all that rich information using substantially fewer tokens, vision tokens in this case.
Fewer than the equivalent digital text tokens.
Way fewer.
Yeah.
Think about it. A single vision token can encode not just the character, but its location on the page, the font, its relationship to other nearby characters. It captures the information density of multiple text tokens all at once.
Ah, okay. So they're essentially leveraging the fact that, our own visual system is super optimized for recognizing dense, structured information in a 2D space, like reading a page.
Precisely. And DeepSeek-OCR is the system they built to prove this concept. It basically has two main parts. First, there's the DeepEncoder, that's the core compression engine, handling the 2D optical mapping and creating that data bottleneck.
Yeah.
And second, there's the decoder. It's the DeepSeek 3B MOE A570M model. It's a pretty compact language model that's specifically trained to reconstruct the original perfect text from just that handful of compressed vision tokens.
Got it. So that framing really clarifies their research goal. They're essentially asking, okay, if you have a document with, say, 1,000 words, what's the absolute minimum number of vision tokens you need to accurately reconstruct it?
Exactly. What's the limit?
Which brings us right to the engine designed to find that limit, the DeepEncoder. Now, when you're dealing with document images, you're talking high-resolution inputs, right? That means a lot of visual data initially. How do they handle that massive image without just creating way too many tokens right off the bat?
Yeah, that's where the architecture gets really clever. They use a kind of hybrid approach to keep both the high detail and the global understanding. They essentially combine two pretty hefty vision systems.
Okay.
They link a SAM-based encoder, the segment anything model, which is brilliant at identifying boundaries and local detail.
A-race the segmentation stuff.
Yeah. And they link that with a CLIP large component, which is trained on massive data sets to understand broader visual concepts and context. Global knowledge.
So local perception and global knowledge working together makes sense for reading a complex page.
Exactly. But the really crucial innovation for efficiency sits right in the middle between those two. It's a 16x convolutional compressor.
A compressor between the perception and understanding layers.
Right. This is the bottleneck that keeps the token count manageable. So get this. Consider a high-res input image, maybe 2024 by 124 pixels. That initially generates something like 4,096 patch tokens.
Okay, that's a lot.
It is, but that compressor reduces the token count by 16 times, down to just 256 intonates. Before those tokens even hit the really computationally expensive global attention components in CLIP.
Wait, hold on. If they're squashing, what was it, 4,000 tokens down to 256,
Mm-hmm.
how do they make sure they don't just lose crucial details, like the fine print in a contract or a tiny footnote? Are they just sort of hoping you won't notice?
Huh. No, that's the clever part of the design. By putting the compressor before the global attention component, they ensure the network only really pays attention to the most salient 256 patches, information-wise. It makes the activation memory controllable and efficient.
I see.
They're basically trusting that initial SAM layer to pull out all the necessary visual features before it gets compressed. It's architectural efficiency, focusing the heavy computation only where it counts the most.
Smart. And for practical use, they mentioned DeepSeek-OCR supports multiple resolution modes. I saw names like tiny, small, base,
Yeah.
even Gundam.
Yeah, Gundam mode. It allows them to precisely tailor the token consumption to the document's complexity. So users can switch, from compressing a simple letterhead efficiently to handling an ultra-high-res newspaper page just by adjusting that compression ratio on the fly.
Okay, that versatility must have been key for testing the limits.
It absolutely was. It allowed them to rigorously quantify the boundaries of this compression. They use their internal tests, which they call the Fox benchmarks, testing documents with varying amounts of text against different limited vision token budgets.
All right, let's dig into those numbers. This is the proof of concept, really. Comparing the original text tokens to the resulting vision tokens, what did they find?
So the key finding, when they kept the original text amount within about 10 times the number of vision tokens, so a compression ratio less than 10x the OCR decoding precision stayed consistently high, around 97%.
97% accuracy at nearly 10x compression.
Yeah. To give you a concrete example for the paper, for documents that had between 800 and 1,000 original text tokens, using only 100 vision tokens gave them compression ratio between 8.5x and 9.7x.
Right.
And the resulting OCR precision was 96.8%, near lossless. This strongly suggests that vision really does allow for roughly a 10x lossless compression factor for document content.
That's impressive. But what happens when they push it past that sort of optimal 10x boundary? Where does it start to break down? What's the failure point?
Well, they did push it. When they went all the way to a 20x compression ratio, so I think documents with maybe 1,200 text tokens being crammed into just 64 vision tokens, the accuracy does drop, but maybe not as catastrophically as you'd think.
Okay.
It still hovered around 60%, which, isn't perfect, but it's still usable for some things.
Yeah.
And importantly, it provides these crucial empirical guidelines for anyone trying to optimize token allocation in vision language models.
Right. It gives you a map of the trade-offs.
Exactly. It offers a very promising path toward achieving that practical 10x lossless context compression using these kinds of text-to-image approaches in real systems.
This really does seem to prove that fundamentally, vision is just a superior way to store dense document information compared to a standard linear text token sequence.
Seems that way.
Now, okay, beyond the experimental novelty, we need to talk practical performance. You mentioned DeepSeek-OCR isn't just a lab experiment, it's meant to be a workhorse.
It absolutely is. They tested it using the OmniDocBench standard, which is, the industry benchmark for measuring real-world document processing speed and accuracy.
Yeah.
And the results show DeepSeek-OCR is highly efficient.
Better than existing systems.
Yeah. It surpasses competitors while using far fewer tokens. For instance, using only 100 vision tokens, it actually outperforms a model called GOT-OCR 2.0, which needed 256 tokens to do the same job.
So more than twice as efficient in that case.
Right. And the scaling differences get even more dramatic when you look at really dense, complex documents.
Like with that Gundam mode.
Exactly. In their high-resolution Gundam mode, using fewer than 800 vision tokens, DeepSeek-OCR outperformed models like MinerU 2.0. Now, MinerU 2.0 typically needed nearly 7,000 vision tokens per page for similar performance.
7,000 tokens per page versus under 800. That's almost a 10x difference again, just in token count for similar quality.
It's huge. And that token efficiency translates directly into massive cost savings and speed advantages in production environments. The paper actually emphasizes that DeepSeek-OCR can generate training data for other LLMs and VLMs at a really impressive scale. They estimate over 200,000 pages per day on just a single A100 GPU.
Wow. That's genuine industrial scalability.
It really is.
And the practical side is boosted by what the paper calls deep parsing capabilities. It's not just reading the text, right?
Yeah.
It's understanding the structure of the information on the page.
This is moving beyond just simple optical character recognition. It handles more advanced, like OCR 2.0 tasks, things like parsing charts and converting them directly into structured HTML tables.
Oh, that's useful.
Very. And critically, it can recognize chemical formulas and convert them into the machine-readable SMILES format. SMILES is that simplified string code for molecular structures. It can even handle simple geometric figures.
Plus, with all that training data they must have used, I imagine the language coverage is pretty good. They mentioned multilingual recognition.
Yeah, impressive multilingual capabilities. They claim OCR support for nearly 100 languages, likely due to training on very diverse PDF data.
Okay.
And importantly, it still retains a solid baseline level of general vision understanding. So the model isn't just a document specialist. It can still describe general images, do some object detection, things like that. It maintains that general VLM interface.
Okay, so we have incredible compression, practical speed, deep parsing, multilingual support. What does this all mean for the future of LLMs, maybe beyond just document scanning? This brings us to what might be the most abstract, but honestly kind of fascinating potential application: simulating human memory.
Right. This is where the paper gets a bit more speculative, but it's really interesting. The discussion links this optical compression technique directly to memory and forgetting mechanisms.
So?
They propose using this highly efficient optical processing for managing dialogue histories, especially ones that stretch way back, far beyond just a few turns of conversation.
Yeah.
You could maintain that 10x efficiency for really deep historical context.
Okay, but where does forgetting come in?
The analogy they draw is key. They suggest that human memory decay over time, how details get fuzzy, resolution fades, is actually analogous to how visual perception degrades over spatial distance. Things further away are less clear.
Ah, I see. Both involve a kind of progressive information loss.
Exactly. And they're proposing to leverage that idea computationally.
How would that work?
Well, they're essentially suggesting we could weaponize blurriness and token reduction to manage the computational load of very old context. The mechanism they propose involves managing older contexts, like past pages of a document or earlier parts of a long chat by progressively downsizing the rendered images of that older content.
So you'd literally make the images of older stuff smaller and lower resolution.
Precisely. This naturally reduces the vision token consumption for that old context, and the text itself becomes visually blurred or less distinct in the representation.
So the blurring isn't a system flaw. It's a deliberate design choice. It's modeling information loss or forgetting over time while keeping the most recent high-priority context totally sharp and crystal clear at full resolution.
You got it. It's active computational management cleverly disguised as natural memory decay, a way to keep infinite context manageable.
That's a really elegant way to think about balancing perfect recall with practical compute limits.
It suggests a really powerful path towards these, theoretically unlimited context architectures that have to grapple with the cold, hard constraints of computation.
So summing up the core contributions here.
I'd say there are two main things. First, the quantitative validation that vision offers incredible text compression efficiency, that 7x to 20x reduction range, with near lossless around 10x. And second, the introduction of that efficient DeepEncoder architecture and the practical DeepSeek-OCR model itself, which proves it works.
It really demonstrates that using the visual modality as a compression medium offers a genuinely scalable solution for the ultra-long context problem in LLMs. This feels like early-stage research that could really set the direction for how next-gen models handle context way beyond what we think is possible now.
It's definitely forcing a rethink about the fundamental nature of information representation in AI. Is linear text always the best way? Maybe not.
Absolutely. And it leaves us with a fascinating final thought for you, the listener. Since this context, optical compression can simulate memory decay by blurring and reducing the visual data of old contexts. It raises a really crucial design question for anyone building these future systems. If we intentionally build an LLM with this kind of simulated forgetting, how do we actually define the policy? How do we decide which historical information gets compressed almost to the point of being gone, becoming just a fuzzy summary, and which vital information must remain crystal clear at full resolution indefinitely? The capability seems to be emerging, but the ethics and the policy behind managing that simulated memory decay, that's a design choice we'll absolutely have to confront.